comments and make.
Welcome to the CERIAS Security Seminar for January 24th. Today we're honored to have our own Professor Wojciech Szpankowski with us. Wojciech has a doctorate from Gdańsk University, where he also spent some time as faculty, also was at McGill University before joining us here at Purdue. Wojciech is an IEEE fellow as well as a recipient of the prestigious Humboldt Fellowship, and will be talking to us today about what is information, talking about going beyond information or beyond information theory.
Thank you very much. Thank you for inviting me here. This is a very general talk, and I doubt we will agree on what is information, but I would like to present to you some things. And where I will go through some characterization of information, and maybe we end up at the end of better understanding information. And I want to show you that information is studied not only in computer science, but also in physics, economy, biology, chemistry, and I would like to show you that information is actually everywhere and it is worth studying. So what is information? I think the best way it was characterized by Carl von Weizsäcker, who make two statements that actually, at least for me, give a very good characterization of information, especially two properties, relativity and rationality. He said that information is only that which produces information. The best, I think, to explain it is through a very simple example. Imagine two guys sitting in a cafe, drinking a coffee, and one actually will continue drinking coffee, and the other guy is actually waiting for a message which tells him at what time a train or a bus will depart. And imagine that the message comes, and then observe activity of these two guys. The first guy, doesn't matter what the message contains, will not change his activity. This message will not produce any information for the guy whose objective activity is to drink a coffee. Why? There will be a significant, a major change in the activity of the first guy depends what the message contains, what time it arrives, and where it arrives. So if it arrives at 5 o'clock and it says the train departs at 4 o'clock, you can imagine that this message does not actually contain much useful information because it's too late. So timing is important. If actually this message arrives not to the restaurant that the guy is sitting, but to another restaurant, so the space aspect of the information, that it also will not be good. It will be different information. So this is a relativistic aspect of information. It depends on the activity of the recipient. There is another aspect, rationality, a rational aspect of the message. Weizsäcker says information is only that which is understood. If I will speak in Polish now, I think you won't understand too much, you as a recipient. However, I will be delivering the same message. And Feynman actually making a very simple statement, which was very convoluted here, but he says the following: information is not simply a physical property of a message. It is a property of the message and your knowledge about it. His example was actually very simple. He said, if you are waiting for information about your paper acceptance and rejection, if you get an email, the first line tells you everything. I regret or I'm pleased. The whole message is there because you have prior knowledge, and this is actually used to discover information contained in the message. Actually, information is physical also, and actually physicists study it for 100 years. And surprisingly, information can do real work, can move this table if I have enough information. I will try to convince you by a hypothetical or thought experiment of Schiller later during the talk. Wheeler, who was, by the way, PhD supervisor of Feynman, he was a guy who coined the term black holes. On his 90th birthday, he was asked to present to the audience, to his students, 5 big questions of science. Big question of science that will shape science for the next 50 years. His 5th problem was it from bit. He was telling us that we have to study information in generality, its physical aspects as other aspects. Shannon, the only guy who actually single-handedly produced the most successful and beautiful information theory, he did it by making one simplifying but very important assumption that semantics for communication doesn't matter. And for communication, information theory produces wonders. We hear computers, and what we are doing is actually because Shannon was telling us how to ship information faithfully. However, the semantic aspect actually haunts us because we still don't understand information contained in shape in biology. These are 2 very important statements. I would say this tells us why we have to go beyond Shannon. Frederick Brooks, for the 50th anniversary of JCM, he wrote a 2-page paper, 3 great challenges of 50-year-old computer science. And here what he said. Yes, Shannon did wonderful thing for us, and this is probably the most beautiful, at least for me, theory. Some compare Shannon to Einstein. He produced good metrics of information in communication system, but we do not have any metric that will tell us how much information is contained in shapes, in structures. We all agree probably that a car is more complex than a bike. More complex means contains more information, but can you quantify it? No, but we have to quantify now how much information is contained in molecules, if we want to understand information transfer in living cells. We, at least for DNA and proteins, we have to start studying information embodied in structures, and we have to find some good metrics for this. For many reasons, because even to fight diseases like bad cow diseases, which is a structural disease, we have to understand what is a good structure, what is a bad structure, and how much information it contains. Actually, Manfred Eigen, a laureate, a Nobel winner in biochemistry, he actually said it very well, that the differentiable characteristic of the living system information, except it is not Shannon information, it's something else. It's a Darwin type of information. And I will try to tell you a little bit what I mean by this. Since my last talk in October, actually, we make a little bit of progress understanding what the difference between Shannon and Darwin information. But definitely we need to go beyond Shannon, even if it was so successful. So, summarizing, there are 4 aspects of information that we must take into account: relativity, rationality, timeline, and then space. This example, I hope, convince you that these are important things. And if somebody would like to make a very informal definition, we can say that information is that what can impact a recipient's ability to achieve the objective of some activity within a given context. It's in English, not math, but at least it gives us, in this sentence, we contain all relevant aspects of information. Activity, objective, and context. Information is not absolute. It depends on all of this aspect plus few more that we will discuss a little later. Okay, can we try to make it a little more formal? Okay, here's one attempt. Let's go to event-driven paradigm when we assume that all world is populated in systems, whether it is a living cell or software agent or communication network. And such a system is characterized by a state, usually vector space, memory context, the number of customers waiting to a teller in a bank, the number of jobs waiting to be printed, and so on and so on. And actually, the state of the system is changed when an event occurs, arrival of a new customer or departure of a job just being printed. Everything actually occurs within a context, and the context could be time and space, actually. And this is important, so we would like to somehow involve context in our definition. And actually, every event has attributes. For example, when a job arrives to a printer, it carries information